I'm going to talk about the work done by a constant force and the kinetic energy of a moving body. Many of you will have met this in your physics, and you'll be familiar with these concepts. One or two of you might not have done, and so I will explain what they mean. We all know that if we have a particle or a body of mass m acting under a force F, then the acceleration is given by F equals ma. We should also know that if we have our particle moving through a distance s, starting with speed u, finishing with speed v, that v squared is u squared plus 2as. Well, I'm going to multiply both sides of that by m, and at the same time, I'm going to divide both sides by 2. Times m, divide by 2. Times m, and divide by 2. Now we should notice that ma is f. And so this equation becomes a half mv squared is a half mu squared plus fs. The first thing that we look at is this little bit, a half mv squared or half mu squared. This is called the kinetic energy. The kinetic energy, which we often abbreviate to Ke, of a body of mass m moving with the speed of v is half mv squared. The next thing that we look at is the little bit here, F times S. This we call the work done. The work done by a constant has to be constant because the equation for v squared equals u squared plus 2as, a must be constant, so F must be constant. Work done by a constant force, F, is the magnitude of the force times the distance moved in the direction of the force. In this case, this is equal to F times S. We shall say more about that in a moment. The units of kinetic energy and work done are joules, which we write just by the letter J. Let's see what happens when we have a force which is parallel to the displacement. There are two possibilities. The first one is where we have a force in that direction and the displacement in the same direction. Force of 6 towards the right and a displacement towards the right. In this case, our work done is force times displacement in the direction of the force. So work done is equal to force times displacement in the direction of the force is 6 times 3, which is 18 joules. And the second possibility is that the force and displacement are in opposite directions. In this case, you have the force of 6 newtons towards the right, but the displacement going in the opposite direction, still a distance of 3, as I did before, but towards the left. In this case, your work done is going to be force times displacement in the direction of the force. Well, my displacement in the direction of the force is going that a ways, my displacement in that direction is minus 3. And that is minus 18 joules. Now let's take a force which is not in the same direction as the displacement. I've got here a force F and a displacement AB. We can think of our displacement AB as a displacement AN followed by a perpendicular displacement NB. so that the distance moved in the direction of the force is the distance AN. This part of it is perpendicular to the force, so there's no component of that in the same direction. If I move through the distance S, it is moving a distance of AN in the direction of F. But if we look at it like that, the work done now by F is going to be F times distance moved in the direction of the force, which is AN, and that is going to be F. AN is S cos theta. Sometimes it's easier to think of it in a different way. I have the same problem here, that I have a force F. My force F at an angle of theta, I can resolve to F cos theta in this direction and F sine theta in that direction. That's just normal resolving of forces. Now, instead of thinking of my force F, I think of two forces. The work done by F cos theta is going to be F cos theta times the distance moved in the direction of the force. So my work done now is going to be F cos theta times S plus, now how much work does F sine theta do? Well, F sine theta, if I go from A to B, I go 0 in the direction of F sine theta. If a force is perpendicular to the direction of the displacement, that force can't do any work. So this is going to be plus 0. And that is just the same as we had before, F S cos theta. So your work done, you can think in two ways. Quite often it's easier to resolve the forces and just look at that. At other times, you want the line of action or the distance moved in the direction of the force like that. And now I want to look at what happens if we have something moving freely under gravity. If we have something of mass m falling under gravity through a distance of h, then the force acting is going to be mg. That will be downwards. It's falling. The displacement will be downwards. They're both in the same direction. The work done is wrong color. So let's change the color. mgh. That is my work done. I now want to look at what happens if we have something moving freely under gravity. Let's suppose we have something, first of all, moving downwards. If it's moving downwards, then the force of gravity is going to be mg. The mass is m, and that will be acting downwards. The displacement will also be downwards, and so we have same direction. The work done by gravity in this case is going to be mgh. Now look at what happens if we have something moving upwards. If we've got something moving upwards, then mg is still downwards, the force of gravity, but the displacement is in the opposite direction. So the displacement in the direction of the force is minus h. So this time we have work done is minus mgh. Notice that when it's falling under gravity, the speed will be increasing, the kinetic or the energy will be increasing, and the work done by gravity is positive. When it's going up, obviously it's slowing down. If you throw something up in the air, it goes more slowly. The work now is negative. The quantity mgh is called the gravitational potential energy, and it's usually written as GPE is equal to mgh. If I can write the h properly. And that you will have met in your physics, those of you that have done it. You probably met it last year anyway.